Okay, this is calculus, section 6.2 on natural logarithms, and we'll first launch into the definition of a natural log by using calculus. That would be ln of x is equal to the integral from 1 to x of 1 over t dt, where x is greater than 0. So this is a little bit different from the pre-calculus definition. Welcome to calculus. If x is greater than 1, then ln x is the area under the curve y equals 1 over t from t equals 1 to t equals x. Now if x is between 0 and 1, then ln x is equal to this integral again, which can be written like this. Negative integral from x to 1 of 1 over t dt. Again, x is between 0 and 1. And this property comes from page 324. Alright, so it's the negative of the area under the curve from x to 1. Now if x equals 1, then ln of 1 is equal, of course, to integral from 1 to 1 of 1 over t dt, which of course equals 0. Now by the first part of the fundamental theorem of calculus, that's found on page 333 in your book, what's the derivative of ln x? Alright, d dx of ln x. Well, what's ln x? It's this integral. So we'll take the derivative of this integral, d dx of the integral from 1 to x of 1 over t dt. You've seen these kinds of derivatives before from fundamental theorem of calculus, and this is equal to basically the integrand, that would be 1 over x. So the derivative of ln x is 1 over x. And from this you can obtain the antiderivative of 1 over x is equal to ln x plus c, some constant. So there's the derivative of ln x. Now you might have ln of something besides just plain x. Well, x can be a part of this as well, what I'm going to discuss next. You can have a function of x inside the ln. Like, for example, u of x could equal x squared plus 2, so you could take ln of x squared plus 2, right? Or u of x could equal x, in which case this would still work, alright? The derivative of ln x would still be 1 over x. But it could be something more complicated, u of x. So what is this? Well, you just use the chain rule, alright? So this is equal to d du of ln of u times du dx. Again, that's the chain rule. And this is equal to, well, the derivative of ln u, according to what we've just done up here, is 1 over u. And then du dx, whatever that is. Or you could write it like this: du dx u prime, right? So you've got u prime times 1 over u, or u prime over u. So if this were 2x, let's say x squared plus 4, ln of x squared plus 4, and you took the derivative, well, that would be the derivative of the inside function, the derivative of x squared plus 4, which is 2x. And that was what you would put up here, 2x over x squared plus 4, that's u. u of x is x squared plus 4, so that would be 2x over x squared plus 4. Okay? And here's another example. This one's a little bit simpler. The derivative of ln of 2x, let's say, is equal to 1 over 2x, u equals 2x, times the derivative of 2x. And so that of course, equals 2, so you've got 2 over 2x, and that equals 1 over x. In fact, the derivative of ln of any constant times x, ax, would be 1 over x. Alright? Another example, the derivative of ln of x squared plus 3. So I'll just use this shortcut here. It's u prime over u, right? So we have u equals x squared plus 3. So u prime is 2x over u, which is x squared plus 3. Okay, now there's a table on page 460. Take a look at that in your book. Page 460, table 6.1. These are properties of natural logarithms. Now these are properties that you should already be familiar with from pre-calculus. If you don't remember these from pre-calculus, you need to review them because, well, I'm not going to go over them since it is pre-calculus. Alright. Now, let's go back to the calculus. The derivative of ln x is 1 over x, and that's positive for x greater than 0, which means that ln of x is an increasing function. Now the second derivative, that is the derivative of x to the minus 1, is equal to negative x to the minus 2, or negative 1 over x squared. Now that's negative, and so the graph of y equals ln x is concave down. So once again, you look at ln x, take the first derivative, that equals 1 over x, and that's positive for x greater than 0. And of course, with the ln function, if you recall, y equals ln x, it looks like this. Notice or remember that ln is not defined for x less than or equal to 0. Alright? So we're assuming x is greater than 0. Alright, so when you take the derivative of this function, ln x, that equals 1 over x, and that's positive for x greater than 0, which is, of course, the domain. And that means that since the first derivative is positive, then ln x is an increasing function. Remember, graphing functions and using first and second derivatives, that's what we're doing here. Now you take the second derivative, and x squared will always be positive here, absolutely, since x is greater than 0 anyway. But negative 1 is always negative, so the second derivative is negative, which means that the graph of this function is concave down, as, of course, you can see. Alright? Okay, let's take a look at something called logarithmic differentiation. It's a nice trick to take derivatives. We're having to assume that the functions are positive, okay, and they're given by formulas that involve products, quotients, and powers. So if you take, for example, the derivative of a rational function, that is a fraction of polynomial over polynomial, right? You have to use the quotient rule, or you could use a modification of the product rule. That is, you can, if you have f of x over g of x, then the derivative, or you can treat that as a product by writing f of x times g of x to the minus 1 power, and then use the product rule. So you can get around the quotient rule on that, but sometimes there's an easier or more rapid way of finding derivatives like that if you use logarithmic differentiation. Now I'm going to look at example 5 on page 462 in your book. We've got y equals, let's say this is kind of complicated, x squared plus 1 times x plus 3 to the 1/2 over x minus 1. And let's say x is greater than 1. Alright? So what you do is you take the natural log, or you could take technically another base, but it's more convenient if we just take natural log on both sides. And again, we're assuming that this function is positive, so the natural log is defined. When you do this in the book, you're not going to have to worry about that because they have the problem set up for you very nicely. Alright, so you take the natural log of both sides of this equation. Well, you apply the properties of logarithms on this side. What you have is the natural log of a quotient. So you apply the quotient property of natural logarithms, right? So that would be ln of a over b is ln a minus ln b, right? So you've got ln of x squared plus 1 times x plus 3 to the 1/2 minus ln of x minus 1. Okay? And now you apply the product property of logarithms here. Ln of a times b is ln of a plus ln of b. So you've got ln of x squared plus 1 plus ln of x plus 3 to the 1/2 and then minus ln of x minus 1. And then you can apply the power rule here with logarithms. You can put the powers in front. So you've got ln of x squared plus 1 plus 1/2 ln of x plus 3 minus ln of x minus 1. Alright, now